anything about any of the three principles of Ramsey theory, Ergodic Ramsey theory, and anything about Poincare recurrence. We still are not fully done with Poincare recurrence. You will see how some not looking related theorems still are proved by way of Poincare recurrence. So I will maybe formulate one of them right now, but we will treat it maybe on Thursday at the next talk. But maybe just to get you even more curious. So here is a famous theorem. So you remember, let me remind you, the Schur's result. So for any finite coloring n, one of Ci contains x, y, x plus y. By the way, Schur I can show to you also as a corollary of Poincare recurrence. Maybe if I will have a little bit extra time, I will do it. But that's hard to see immediately where is Poincare recurrence here, but it is, okay? And now Schur theorem has a far-reaching extension. And maybe since we discussed philosophy of Ramsey theory yesterday, maybe from point of view of this philosophy, it's good to see how one should attempt to generalize Schur. So we said that you cannot destroy arithmetic structure of n, so additive structure of n. No matter how you try, you will get x, y, and x plus y in the same color. But that's maybe only beginning of some bigger type of results. So how about getting monochromatic? By the way, that's convenient language. So things which would be in the same color we call monochromatic, okay? And sometimes you can abbreviate it to mono. This is Greek letter he, which in America is pronounced chi. But so monochromatic comes naturally here. So how about getting monochromatic x, y, z, x plus y, x plus z, y plus z, x plus y plus z? Is there a chance for that? Let's vote. Who thinks this is true? Okay, and who thinks it's not true? Okay, so by democratic rule, it should be true, because no one voted against, and quite a group here, quite a large group voted for it, and it is true. But it turns out, while I can prove to you Schur theorem just by using Poincare recurrence, the next thing already is non-trivial. Already this little thing, so we are getting, so in Schur it was 3 elements. Here it's 7. Maybe we can keep going. How about x, y, z, w, and all pairwise sums, and all triple sums, and all the sums? Okay, so we are about to try to generate as much as possible of elements by using x, y, z, w, and so on as generators. So we are really aiming now at getting a sort of generalized semigroup in one color. Now, it's a little bit too good to be true. It is true, okay? And so I will formulate to you the rightly general result. So theorem, and this is Heinemann. Uh, 1972. And it says this: for any finite coloring of integers, one of Ci's contains the following creature, contains all possible finite sums of some infinite sequence. And so it means That's really something which is hard to believe. But that's exactly the content of Neumann theorem. So let me interpret it again for you. This is a sort of approximative semigroup. You can think of xi's as being its generators. And fs stands for finite sums. And so you take all possible finite sums of generators. There is only one thing which you should not try to do. You cannot take an element, a generator plus itself. My indices are different. So that's an exercise why we should not be too greedy, okay? So you cannot, in general, plan to have element and twice the element in the same color. That comes by simple example, okay? But you always are promised to get an infinite sequence together with all possible finite sums. And pay attention, sequence is infinite. Okay? Any questions about formulation of Neumann theorem? So that's an example of a rare situation when you get not only arbitrarily large finite sets, but in this case it's an infinite configuration. And it's very structured. I repeat, the best way of seeing it as a generalized sub-semigroup. And it's always there in one color. Now, guess what? We will show maybe on Thursday that this is also corollary of properly interpreted Poincaré recurrence theorem. So Poincaré recurrence theorem has a lot of interesting applications. Both Schur and Heinemann are corollaries of the same argumentation, I would say. Okay? But this is not my today's talk. I just wanted to keep you being interested in attempting to understand how in the world the ergodic theoretical methodology of recurrence alone on level of Poincaré still can get so diverse things. We last time saw this lemma of Hilbert. By the way, Neumann theorem generalizes Hilbert's lemma as well. I hope it's clear. You remember what we got last time? We got those affine cubes, I would call them. So finite sums of finitely many elements, but possibly shifted. That's what Hilbert needed, and that's what we proved by iterating Poincaré recurrence, and it was easy, but we iterated Poincaré recurrence in Z itself, not in abstract measure space, if you remember what we did. What? No. What I talk about this, it was this statement which, when we iterated it a few times, we got Hilbert's lemma. And Hilbert's lemma, if you don't know, some of you don't take notes, but I don't know how I called it Hilbert's lemma. Hilbert's lemma is also a special case of Neumann theorem. So Neumann theorem is simultaneous generalization of Hilbert's lemma, which gives you finite sums up to a shift, and Schur, which gives you not shifted but just triple. And Neumann tells you that it's infinite sequence, you don't need shifts, or this will be self-shifts, okay? So it is infinite sequence together with all possible finite sums. Now, I would not be promoting this theorem so much if it would not be, in addition to being beautiful, if it would not be very useful. So what we will see, but not today, that there is a new type of ergodic theory. Today I will keep talking about traditional ergodic theory, which is ergodic theory of uniform distribution. And that's what I will move to now. And you take Cesaro averages of all kinds of natural expressions. They have meaning, physical meaning, and indeed they apply to number theory as well. But it turns out that you can introduce totally new notion of convergence, which is based on Neumann theorem. And this is a sort of a very powerful thing when it comes to all kinds of recurrence results, and it makes many things much more refined. So the best achievements of theory of multiple recurrence, and we will be getting there later today, are through Neumann theorem, as a matter of fact, as a tool for taking limits. Okay, so you still should not see what I mean, right? So it's just only a sort of a, like in Greek drama, you know, before they start the performance, they already tell you who will be killed. So I'm telling you that the best achievements of ergodic theory of multiple recurrence are actually through IP convergence, and this comes through Neumann theory. Okay. So now let's go back to the announced topic of today's talk. So this is uniform distribution. And so just to put everything to common denominator, I'm sure that the following definition is well known, but I still start with totally classical definition. So definition, so a sequence xn in 0-1 interval is uniformly distributed in 0-1 if for any subinterval the following happens. No, I wrote limit, so equals. Okay, and I assume that you all saw such a thing before, but I still think that there is something to discuss here. So do I write too small letters? Should I write bigger? You all see what is written? So here's the probabilistic interpretation. If you shoot points xn to 0-1 interval, then they will appear with equal probability in any subinterval of fixed length. Or in other words, for example, if length of this interval is, say, 1/10, then with probability 1/10 or with frequency 1/10, they will appear in any fixed interval of this length. Okay? Now, this definition is due to Hermann Weyl, approximately 1916, and it helped him to get something which Hardy and Littlewood were working hard. It's a uniform distribution of some polynomials, mod 1, and we will see in a moment how one gets it. But I still want to sharpen the point that this is not obvious at all, at least a priori, it's not obvious at all that uniformly distributed sequences exist. Okay, so let's just look at this definition again. My sequence is uniformly distributed if it gets to any subinterval with correct probability. But how many intervals are there? Even if you fix the length, suppose you fix the length which is 1/10. Imagine there are uncountably many intervals of length 1/10. And to each of them you have to get with the right probability. Is it possible? Well, it is possible, but is it intuitively possible? I don't think so. I really suggest that you try to analyze it. There are good reasons why this is true, but I think your immediate intuition maybe should now have a problem, right? Because there are uncountably many intervals, and in each of them, you spend 1/10 of your time. Well, not you, but the sequence, okay? So there is something paradoxical here. And not only that, but for any length it happens, okay? I think it's interesting even for fixed length, but even for any length, that's a little bit too good to be true. It is true, okay? And so this stronger notion allows you to easier treat all kinds of sequences whose denseness is not necessarily obvious, okay? So in number theory, they traditionally were interested in sequences like n square alpha mod 1. And so example of n, by the way, I said uniformly distributed, and equivalently I can say equidistributed, and it's all the same, okay? So example of a uniformly distributed sequence That's the easiest example, maybe, and alpha mod 1. Is notation mod 1 clear to us? Mod 1, this is the same as n alpha minus n alpha integer part. And it is the sequence which you can prove that it's uniformly distributed by using just this definition. So that's an exercise.
But that one is intuitively obvious. There is no interval which is, if you are not heavily distributed, there will be an interval where you have that limit doesn't exist. But there are no.
No, first of all, it may exist but be different. That's also possible. Maybe it exists and is different than what you expect.
You should have an interval where you should be able, if that doesn't happen, you should have an interval where it's like it's just special, right?
True, but there are sequences which are very nicely dense and still, no, you're right, maybe you have good enough reasons to believe this is so, but what I'm saying that there are sequences which are dense, all right, in 0-1 interval, but not with respect to this uniform measure.
But here I'm not talking about denseness, it's more, right?
Okay, but if they are dense, but uniformly distributed with respect to another measure, so you can measure it by taking limit. Limit will exist, but it will not be length of the interval. It can be some other function of the length of the interval, and there are natural examples of this kind. So I think I can give you some examples right away. If you take an alpha, this is denoted an alpha fractional part sometimes. And that's definition. And if you take an alpha fractional part squared, that already changes the distribution. It will be still dense, limit will exist. I'm not sure how your intuition will compare an alpha fractional part with an alpha to power 1 plus epsilon fractional part, okay? But it will be changes in the measure which measures the...
I'm not saying that. I'm saying that n alpha, that one is an example. You say that it's not intuitively clear that you have it exists. That one is an example. I don't know how to prove all of them.
Okay, so since I did write that is an example, I of course agree with you. All I'm saying that you will have to work to prove it.
Yeah, I think a good reason that this is an example is that, first of all, it's dense, and then you have translations that send the set of values of the sequence in one interval to the set of values of sequence in a dense set of translated intervals of the same length up to a finite number of terms.
So let's then, I didn't want to generate too much discussion of a simple example. What I'm saying, the definition uses uncountably many pairs A, B. And I'm not sure that our intuition, whatever strong intuition you have, easily works with uncountable sets, okay? And that's why I still repeat that you should be a little bit careful without checking.
Yeah, but if it works for interval with rational
So then starts mathematician's job. So first of all, you may observe that it's enough to check it for rational ends. Even then, you will have infinitely many of them, but it's already countably many, and even this you have to do. And then you have to do some approximation showing that if you get it for rational ends, it's for any end. So in other words, it is a decent exercise for an undergraduate student, but I don't agree that this is so automatically obvious. Okay? But if it is, great. So you have healthy intuition, which is very good. And by the way, now that we have this example, so we can then, let's do it without me, or maybe I will write just to record it. So for Neumann theorem, you show that if xn is dense in 0, 1, then there exists a rearrangement such that the rearranged sequence is uniformly distributed mod 1. I see you keep talking about the same thing. Let's do it later, okay? Just maybe you want to challenge yourself with this thing. By the way, I write uniformly distributed mod 1, but since I started with 0, 1 interval, uniformly distributed in 0, 1. And now, is that theorem obvious? Von Neumann published it in Hungarian language, and being von Neumann, he was enormously fast and strong mathematician, but he spends at least 5, 6, 7 pages to do that. Yes, and no, let them do it, come on. So let's, what? You mean the solution? Right. So the moment you have an example, my point is that if you have an example, that's one of many solutions. I'm not sure if it is for Neumann's solution. But if you know an example, then you can do it for any dense sequence, okay? And I leave it to you to think how. Okay. Now, there is one more notion. It's called well distribution, which was, strangely enough, not noticed by Weil, and which appeared only in 50s or 60s. And so a sequence is called a sequence xn is well distributed if for any subinterval lim1, the number of elements, n such that xn is in AB divided by n. Let me do it differently. Sorry, I could do it number of elements where n is between n and m such that xn is in AB divided by n minus m plus 1 equals b minus a, where the limit is now as n minus m goes to infinity. Is this definition clear? So it has uniformity. In addition to limit to be correct, it doesn't matter where you average. So instead of averaging from 1 to n, you can average from n1 to n2. As long as the averaging interval is long enough, you will be in vicinity of the limit. So what your intuition says is n alpha well distributed for any irrational alpha? Irrational? No, I'm glad that you're careful. It is, but it's even less obvious. It is uniformly well distributed, but now it turns out that one has to be careful indeed. And this all connects to ergodic theory. So now let me see where are instances of these notions in ergodic theory. So first of all, here is a von Neumann theorem. But before maybe we go to von Neumann theorem, maybe let us give some equivalent forms of uniform distribution. So the difference so far is only uniformity of the limit. So, but some equivalent forms of uniform distribution. So first, for any f in C01, 1 over n, f of x n converges to integral f dx. And 2, so that's very convenient to interpret as leading to Monte Carlo method of calculating integrals. You know how they calculate? I don't know if they do it today because computers are so fast. But in principle, if you want to calculate your integral, and especially if it's multidimensional, and all these things have multidimensional analogs, all you have to do is to take random sequence, random in very generalized sense. It may be very deterministic, but randomly behaving, like n alpha mod 1. And then you calculate your f at these points, and it should approximate the value of your integral. Okay, and to see that, let me write one more. So for any h in n, 1 over n e 2 pi I h xn converges to 0. And this sometimes is called Weil criterion. What is so good about this Weil criterion is that you have to check only countably many functions. These are exponents. Now, if you believe in Weil criterion, then we already see right away why you were right about n alpha mod 1. Because for sequence n alpha, you will get so-called lambda to be e 2 pi I h alpha. And then lambda to the n will be e 2 pi I h n alpha. And I hope it's totally clear that this sequence goes to 1 if lambda is 1 and to 0 if lambda is not 1. And in particular, pay attention, my lambda depends on h. Okay, so there is something about rationality which I am putting a little bit under the carpet. But for lambda, which is not root of unity, and alpha is irrational in our consideration, that's why lambda is not. Okay, so let me then, instead of, so this will go to 0. Let's call it lambda sub h. And this goes to 0 for any h in n. And I hope it's clear why, because this is just geometric progression, sum of geometric progression, and you can easily sum up those lambda to power n. And the fact that alpha is irrational allows you to see that this is not a periodic sequence. In any case, that's one of many ways of seeing why n alpha is uniformly distributed. By the way, there are versions of all these results with uniformity n minus m, and then it applies to this one in particular. So n alpha is actually well distributed, and it follows from appropriate form of Weil criterion. Any questions so far? I'm going easily between uniform distribution and well distribution, but we should start soon distinguishing between them because it's very hard for a sequence to be well distributed. And we are lucky that there are still good examples. So maybe I should say a few words how to prove all these things. You see, continuous functions can be approximated by step functions. And so this can be interpreted, I don't know, call it star. This formula star means that 1 over n 1 sub ab of xn converges to integral of 1 sub ab, which is b minus a. I hope that's pretty obvious. Is it? Okay. This function takes values only 0 or 1, and it will be 1 exactly when you get inside this interval. So definition of uniform distribution is written only differently and is the same here. And if it's true for such step functions, it should be true for their linear combinations. These combinations in rightly chosen metric will approximate any continuous function, and that's how you can get this. Now these functions, now I will cheat a little bit, so be careful. I'm going to slightly cheat and you should catch me. But I'm explaining now why this is also good enough. So these are exponents. And so by one of the forms of Weierstrass theorem, linear combinations of exponents, or what is called sometimes trigonometric polynomials, are dense in this space. And so if you have it for all exponents, you will have for their linear combinations, and hence for any continuous function. Where did they cheat you? No, it's not uniformity. I was dealing with 1 over n. Same argument applies with 1 over n minus n. All right, it's late in the day, so I will tell you where I cheated you. But it's repairable. I cheated you because those exponents, they have the same value at the end of the interval. They're periodic functions. And here my claim is that it's good for any f. Okay, so you cannot directly apply Weierstrass approximation. You still have to do additional little argument, showing that what happens at the ends of the interval is not so important. Okay, so there is still extra work to be done. Okay, I sharpened the point where I cheated you. I maybe didn't explain it fully, but that's food for your thoughts. Okay. In any case, we will take for granted all these convenient criteria, and this is a especially convenient one. But now, what is the connection to ergodic theory? And it turns out, and I strongly believe that Weil was just unlucky. Weil, the person who should discover ergodic theorem should be Hermann Weil, because he had correct form of ergodicity, philosophically speaking, already in 1916 when he introduced that notion. And as you know, so definition due to Hermann Weil, 1916. And von Neumann came with his ergodic theorem only in 1931, so 15 years later. And now, why do I say that Hermann Weil, in principle, could? And he, by the way, was a very cultured mathematician, so he knew about ergodic problem, coming back to Maxwell and Bolzano and Boltzmann. But so let's look at this definition. That's already in Weil's paper, this equivalent form. And it is this statement which has all the features of ergodic theorem. So let us interpret it properly. On the left, you have time average. You throw this point xn every second to your interval. And this is time average of your measurements. And this is space average. My space has measure 1. That's why it doesn't show. I should divide by the measure of, I should take integral over the space and divide by measure of the space. But measure of the space is 1. So this is an instance of this overarching principle in ergodic theory, and I believe going much even beyond it. The time averages in some decent situations, time and space averages are the same. And that's the content, one of interpretations of the content of Weil equidistribution. And now we can apply this to ergodic situation. And in ergodic situation, you have, so ergodic theorem 1 over n, f of t n x converges to if t is ergodic. Converges to integral of f d mu. Pay attention. I shouldn't say 0, 1. D mu over specs x. So here f belongs to, choose your favorite space. I will take L2, but it's one of many spaces I can choose, of x b mu. And I assume for convenience that measure of space is 1. And then this is Ergodic Theorem, but I have to confess I formulated a little bit sloppily. So where is the sloppiness? Yes, please. What? I didn't mean, thank you, but I didn't mean that. That's genuine typo. But I still say that I formulated it sloppily. So you can tell me why? What you say?
You didn't say convergence. In which sense?
Very good. Right. So I didn't say in which sense convergence takes place. And as a matter of fact, there are many senses in which it takes place. One of them would be in norm. And this is exactly for Neumann. And another notion would be almost everywhere. And this is Birkhoff. And there is interesting history. Who was the first? It was von Neumann, but he did it in norm. And then Birkhoff heard of this. And so von Neumann's achievement was to establish mathematical statement which corresponds to ergodic hypothesis. Ergodic hypothesis was vaguely formulated many times, and it was about time and space average being equal. But physicists believe that it's always the case, and comes von Neumann and explains that it's the case only when T is ergodic. And if and only if, really, if you want it to be for any f. And then you can improve it by putting point-wise convergence. It is harder result to achieve, at least in this situation. And von Neumann is much more general. It works in many spaces, in spaces where you even don't have point-wise convergence equivalent. Okay, so von Neumann is maybe today I could say that to multiple recurrence von Neumann applies better. But for physicists, maybe to have point-wise convergence, or indeed not point-wise, but almost everywhere convergence, because not always you will have everywhere. Okay, and so it was Birkhoff who proved it in this sharper form, and it was unpleasant situation when Birkhoff started promoting his result before von Neumann published his result, and you can read about this in existing literature. And it's sad that a big and already not young mathematician Birkhoff was so excited by his getting right on von Neumann's innovation that he even didn't want to let von Neumann to get some glory first. We all don't do this right today, but Birkhoff was not so right about that. So you can read about this, and it's an interesting story. Von Neumann was very sad about that. He was young, aspiring mathematician, fresh emigrant, or maybe almost emigrant. For him, it would be more important. But in any case, that's where suddenly interesting difference between well distribution and uniform distribution come into play. Thing which, strangely enough, was not noticed by von Neumann and by Birkhoff. But for Neumann theorem, and so let me then formulate von Neumann properly. For Neumann theorem is about this. 1 over n minus m. So von Neumann theorem has elements of well distribution. And when you start asking same question about point-wise convergence, or more precisely almost everywhere convergence, that's just not the case. Okay? And in my opinion, that's maybe, and they had interesting exchange of little articles, each claiming that his theorem is better for physics. And you may want to just go to internet and see what von Neumann and Birkhoff published in 1932. So Birkhoff published his theorem in December of 1931, and then von Neumann rushed and published in January 1932, and then it was a few papers that year which are very interesting to read. Okay? In any case, von Neumann theorem has extra element. This extra element is uniformity. And let us apply it now to our old problems related to Poincare recurrence. Now we'll see that it helps to seriously improve Poincaré recurrence theorem. Let's see how. But so here what we can do. So let's consider again this expression and assume for a moment that T is ergodic. We will remove this assumption in a moment. So this goes to integral of f d mu. And if I put f to be 1 sub a, so put f to be 1 sub a, multiply by 1 sub a, and integrate. Let's see what will happen. So first of all, my expression will become 1 sub a and 1 sub a t and x. This should go to 1 sub a. So we assuming that t is ergodic for now. And so this should go to this integral. Is it clear what I'm doing? I just took f to be a indicator function of a set. A is just some set in x. Measure of a, we want it to be positive, but so far I didn't need positivity. Is it clear what I'm doing? I just take 1 sub a instead of f. Then the limit should be integral of 1 sub a. And by the way, this is the same. This thing is measure of a. I hope it's obvious, right? If you integrate in the indicator function of a set, then you get its measure. People, I see by your faces that you're not with me. What is wrong? Do I write too small letters or what? Should I write bigger? I don't know. Let me try again. One over n minus m integral, not integral yet, 1 sub a of t and x converges to integral of 1 sub a d mu, which happens to be mu of a. What is not clear about this? I just substitute very special function instead of f. Are we okay? And now I can still multiply by 1 sub a and integrate again. Oh, maybe that's what is missing. My integral was missing. That's why you were suspicious? What? Don't. Sum. And sum was missing. Okay. It was long day. Okay. Then I didn't have to write in big letters. Okay. But now we are comfortable, I hope. And now look what we got. Integral of this is product of two indicator functions. This is the same as 1 sub a. You may want to check why, but it's easy. And so what we got out of this, that 1 over n minus m, mu of a intersection t minus n a, converges. So this was mu of a, and I integrated again, so it's mu square of a. I could take instead of second function b. In ergodic case, things are okay, but I'm interested in Poincaré recurrence, and I'm going to drop assumption of ergodicity. So one can show this is not too hard. Is that if T is not necessarily ergodic, then one lim of 1 minus m mu of a t minus n a is always bigger or equal than mu square of a. Please look at this theorem. Does it remind you something I wrote last time? Yes, what? Mixing? No, because its average You see, if I would be as forgetful as before and forget about summation, then it would be mixing. But no, it's average. It's Cesaro average. Hinchin, thank you. So let's derive corollary from this. So since I repeated those things here, I can erase here. If you look at this theorem, and because of the well distribution, which is due to n minus m business, you see that no matter what is your system, I even removed, you see, it's not obvious, by the way. Be careful with such things. Here it works. Some other times it doesn't. But if t is ergodic, then the limit is correct limit. And surprising thing is, and I don't believe, again, it's so easy to see intuitively, but I trust your intuition. But the fact is that when t is not ergodic, then you actually cannot get worse. It's only better. And be careful with your intuition. If you think that t is not ergodic, means it doesn't move some things. Okay, so if for some set you get extras, then for complement, you still will get extras. Okay, so it's interesting. In any case, that's the correct statement. And let's only interpret it. It remains only to interpret it. And we will get Hinchin's result. So as long as you took long enough interval, you should be an average there. You should be, and you're averaging positive numbers, not negative numbers, and then you should be in epsilon vicinity of this limit. But if average of no negative numbers is close to mu squared, then at least one of them will be. So it shows right away that, so corollary of von Neumann theorem the set of n for which mu of a intersection t minus n a's, and this is for any epsilon, bigger than mu square of a minus epsilon, has bounded gaps. Or we call it synthetic. Is the statement, and the way we derived it, clear? Is it totally clear? I will be glad to repeat the argument. It's a simple argument. Is it clear that it follows from this? In form with inequality, I don't need ergodicity. Yeah, so for any x, b mu t, for any a of positive measure, for any a, and for any epsilon, these are the assumptions. Okay? Any questions? So you see how powerful is von Neumann theorem. It allows you to improve on Birkhoff's theorem. Indeed, by the way, it's also improvement on Hinchin in a way, because Hinchin is satisfied by just having good ends being synthetic, and we see that there is plenty of regularity about such ends. But the truth is that Hinchin proved it in this form. Okay, so Hinchin just was interested in applying it to improvement of Poincaré, and what he did, he just reproved von Neumann theorem. So credit should be given to him. Okay? Now, this is still not the best improvement of Poincaré recurrence. And again, we see that, okay, this is large set, all right. But I said it already yesterday, and it remains a problem. Okay, this is a synthetic set. And suppose I take some other system. It will be mu1 of a1 intersection t1 minus n a1. I will be interested in getting n's for which this is positive, and this is again synthetic by the same theorem. But if I take these two sets, take this set and this set, do they intersect? It's not too hard to see that they do, but you have to do something about this. A priori, they don't. So all I'm trying is to stress that syntheticity keeps not being satisfactory property, because just by establishing that the set of returns are synthetic does not automatically imply that these two sets intersect. And this would be nice, by the way. So you have two totally different systems, two totally different sets. This set comes back, this set comes back. Why should it happen simultaneously? Now, of course, you can take so-called Cartesian product system and do something about this. So that's a way of, establishing that these two sets will intersect. But it still does not help. Suppose I'm interested in good intersection, not just positive intersection, then even the product of sets is problematic. Okay, so in other words, there is what to improve here. And we will improve it when we start applying Neumann Theorem. So Neumann Theorem is here in the background, by the way. If I want to start doing things better, I should take limits which are different from Cesaro limits. But today we stick to Cesaro limits. And here's an interesting thing. So now I just mentioned in passing that similar things happen, similar for well distribution. We will come back to well distribution. But I should give you some maybe more examples of sequences now. And one of my topics for today is van der Corput sets. So I want to define them. That's, by the way, so far, these are pretty classical things by now, and I wrote about them in my surveys, but van der Corput sets are less known, and I think they deserve to be better known. So I will define them in a moment. Any questions so far? So we'll come back to this. I want you to remember that we did see how Hinch recurrence follows from von Neumann theorem, and in a stronger form in a way, because for Hinch something less than this would be still enough. The fact that limit exists is important. But for now, I will erase these things, okay? So maybe example. So one more definition. So definition. A subset S in N is called a set of recurrence if for any measure-preserving system and any A, there exists N in S such that measure of A intersection T minus NA is positive. So I want, since we are interested in Poincare recurrence, why not to start being interested in sets along which you achieve it? And this is maybe only beginning of some line of investigations, because similarly to Poincare, I may be interested in sets of nice recurrence if I get big intersection, right? That's not part of this definition, but it's not obvious if this is the same definition. If I would improve quality of recurrence, right, I could want this measure to be large. And for applications, that would be useful. So for now, I just will be happy if I come back to my set, okay? Any questions? Questions? Is it clear that it will be maybe different definition if I will demand here good size of intersection, okay? I don't at this stage. Examples. Let's see, some examples just follow from what we did. You remember when we proved Poincare recurrence, the proof itself suggests examples. Let me repeat the proof for you, just for you to guess some big family of examples. How did we prove Poincare recurrence? We took A, T minus 1A, T minus IA, T minus JA, and then we observed that two of them have to intersect for some I and J, and then measure of t minus IA, which is the same as measure of A t minus, and this is positive, and this is my n, and that's the proof of Poincare recurrence we gave yesterday. But if you are a little bit more careful here, you will see that we didn't use the fact that I take all the powers of t. I could take any sequence, take any, say, increasing sequence, and consider t minus n1a, t minus nia, t minus nja, and so on, and just repeat the same argument. So if you have two sets with non-trivial intersection, and these all sets having the same measure, then you will get that measure of A intersection. So there exist I and j, so that measure of t minus nia, t minus nja, which is the same as measure of A, t minus ni minus nj. A is positive. Is it clear what we did? We didn't work too hard. We just observed that the same pigeonhole principle applies to any sequence of powers. But it suddenly gives us non-trivial results. So any set of differences. So something of the form ni minus nj, I bigger than j. For some sequence, say going to infinity, it's not so significant. Is it clear? It's a corollary of the proof. We didn't work too hard to get it. But see, suddenly it gives us interesting application. But maybe I should give you a little bit more examples. So this was first example. And second example is, which I mentioned, n squared, or more generally, polynomial of n. And I provisionally put, so polynomial should be with integer coefficients and 0 at 0. It's provisional, because we happen to know necessary and sufficient conditions for polynomial to be good for Poincare recurrence. And I'm not sure you can guess it. I could challenge you to try to guess it, but it's not totally obvious a priori, because there are some phenomena with polynomials which show up only with polynomials of degree 4 or 5 or 6. In any case, these are already impressive examples, but the first one was nothing, right? We just observed what we did in the proof and applied it. But I claim that because of this quantifier, you see this quantifier? Any. We can get interesting corollary now. So we'll do it right away. But so we have by now, can I say that? We have by now uncountably many examples of sets of recurrence. Just for you to feel easier about this uncountably many statement, I will give you one more, 3. N alpha integer part. Or if you want, n square alpha integer part. There are many, okay? And alpha is any. Now I think we believe that there are uncountably many examples, right? Question? And now these examples are funny. They're already not really easily analyzable same way, because you can say, those of you who know that n alpha is uniformly distributed, or those of you who happen to know that n square alpha is uniformly distributed, may think that some of the reasons for recurrence is some connection to uniform distribution. And that's actually my topic today. But uniform distribution is not the only source of recurrence. Okay? Sets of differences arguably are not uniformly distributed when you multiply them by alpha. It's easy to see. And yet they do give easy, immediate example of a set of recurrence. But so let me just get the corollary of this, which is interesting. Any questions so far? So I think I can erase this. I just repeat of the proof of Poincare recurrence, right? Okay. But then I will have to introduce one more definition. And so let's call it delta star, okay? So definition. A set E in N is called a delta star set if for any infinite Ni in N delta, E, say for convenience, and I going to infinity, E intersection and I minus Nj is non-empty. Now we are starting new approach to notion of largeness. You remember yesterday we talked about notions of largeness? So we had large sets as subsets of some structures. But then I was promoting the idea that certain configurations come about along super large sets. And super large sets, as it turns out, is easier to define by intersectivity property. So let us spend a little bit time on this. It may be new for some of you. You see what I want from E to be delta star. It should non-trivially intersect any set of differences whatsoever. It should be some notion of largeness, right? It cannot avoid sets of differences. For example, set of odd numbers does not have delta star property. Is it obvious? Hope it is, because even numbers is set of differences, and odd numbers don't intersect. So odd numbers is a synthetic set, yet it's not as large. But a priori, by the way, it's not clear if delta starness implies syntheticity. That's your exercise. If E is delta star, then E is synthetic. And moreover, there are synthetic sets which are not delta star. And we just gave example right now. It's odd numbers, say. Now, it remains for me, if I can take for granted this exercise, then it remains for me make just the following statement. The n for which measure of A intersection T minus NA is positive is delta star. That's here. Just put together all we talked, and you will see it right away. N's along which I come back and intersect my set can be chosen from any set of differences. So it's delta star by definition. Okay, are you with me? Actually, for any epsilon bigger than 0, here's pleasant addition to this. How do you like this statement? Even this set is delta star. That's already not so bad because it improves Hinch recurrence again. You see, Hinch recurrence says that this set is synthetic. We saw it follows from von Neumann Ergodic Theorem. To use von Neumann Ergodic Theorem, now I'm very interested in very general situations. Suppose I have action of any group whatsoever. Then I may not have even von Neumann Theorem. There is always some version of a Neumann theorem, but in principle, people who do ergodic theory, they used to think that von Neumann type theorem is true only for amenable groups. Whatever amenable is, I will tell you later in this course. And for amenable groups, ergodic theory goes on pretty well. So if you know what are amenable groups, for amenable groups you can get similar argument through von Neumann theorem and get Hintschen-like result in any amenable group. But first of all, not every group is amenable. And maybe Hintschen result is more basic than that. Indeed, it's so much more basic that it's even can be proved in a stronger fashion, and that's what we did right here. Now, what you need for this we got for free by examining the proof of Poincaré. This is not for free, but it's based on exercise I gave you yesterday. It was an exercise that if you have a sequence of sets of equal measure, then two of them have nice intersections. You remember? It was formulated at the end. If you apply this theorem, and this is a couple lines of some good argument, then you will get this corollary. And now there is one more thing which I have to say. Fact is, if E1, E2 are delta star sets, then E intersection E1 intersection E2 is also delta star. And that brings our formulation, our improvement of Hintschen recurrence to convenient form. Because now the ends which bring your set back, and even with large intersection, are improved to quality which has filter property. That's delta star. And there are many other filter properties. Delta star, unfortunately, works only that far. Suppose I would want to check things related to polynomial recurrence, other thing, multiple recurrence. Delta star fails to keep working. But idea is presented here. And let me just stress this idea of how one introduces large sets. That, I think, is the most interesting philosophical thing. By the way, like many things in this area, it goes back to Furstenberg and his co-workers. So he started himself and then had a couple very fundamental things with Benji Weiss and Izzy Katznelson. And in one of these papers, the notion of this star business, I think, appears. It definitely appears in his book. And so the star idea... What? Which one? Ah, you want a hint? I can give a hint. I will give a hint. Hint is that you should use Ramsey Theorem. After all, this is Ergodic Ramsey Theory. So so there is a theorem due to Ramsey. I don't want to start formulating it because everyone knows it from classical combinatorics class. If not, I will tell you next time if you will keep being interested. But it's trivially searchable on internet. So use Ramsey's theorem. Not Ramsey theory, but Ramsey's theorem. And you can get it, okay? So sets of differences, and I will hint even more. Sets of differences are about ij, right? So they're about two-element subsets. Okay, so I gave you enough hints, okay? So you have to apply a form of Ramsey's theorem and you will get it, but that's nice on its own, right? So you have a filter property, and we're interested in applying to combinatorics. Why not to use combinatorics sometimes back? So Ramsey's theorem gives you filter property of delta star sets. Delta star sets improve on Hintschen. So it's really a nice game. Now, since I wanted to talk about van der Korput sets, I had to do all these definitions because van der Korput sets are more esoteric, but as you will see, they are connected in some not totally clear way to sets of recurrence. So what are van der Korput sets? Before I will tell you what are van der Korput sets, I will tell you what is van der Korput trick. And again, it's a well-known thing, so you can find details in my surveys. So van der Korput trick. if, and by the way, in my definitions, I took sequence to be in 0-1 interval. If it is out of 0-1 interval, I take it mod 1, okay? And so I may sometimes forget to stress it, but sequences which are not in 0-1, I always can take mod 1, and it will be back in 0-1 interval. And so I will be formulating it now in this terminology. If xn is, no, if for any h in n, xn plus h minus xn is uniformly distributed mod 1. So, repeat, my sequence is somewhere in R, but I talk about mod 1. So I take this sequence and take mod 1. Then xn is uniformly distributed mod 1. So it's called van der Korput trick, but it was already in disguise already in the original paper of Weil. And why did Weil need it? So here is a corollary. So we will take it for granted, okay? You may want to think why this is true. In order to understand it better, you will need maybe to use this criterion. Let me not do it now. It's nicely written, and you can find it in my service, and not only in my service. But let's see how useful it is. So it's a so-called van der Korput's difference trick. All you have to do is to do differentiation of your sequence. If the differentiated sequence, now I'm putting some philosophy, be careful with this philosophy. So xn plus h minus xn is a sort of derivative, discrete derivative with step h. And if you take derivatives of your sequence, and each time you get a uniformly distributed one, then xn itself was uniformly distributed. That's the content of this trick. And now, and exactly. And so that's I was expecting somebody to say, thank you, Google. So if that's the case, if differentiation is really meaningful there, then it should be good for n square alpha or any polynomial. Let's see how. So I think I want to erase things. Maybe I will erase it here. All right. So we saw that n alpha is equidistributed all right by using just geometric series. But if you try the same thing with n square alpha, it will not work so easily. To estimate trigonometric sums along polynomials is an old and important area, okay? But van der Korput allows you to somehow in sneaky way to get around. So consider xn to be n square alpha, where alpha is not in Q. And so let's do some small calculation. And I'm omitting mod 1 all the time. I hope we are comfortable with this now. So this is n plus h square alpha minus n square alpha. And this is n times 2h alpha plus h square alpha. And what do we see? H is fixed. So this is a constant. And this is, as we know and agreed about, is uniformly distributed sequence. Hence, conditions of van der Korput trick are satisfied. And the immediate corollary, and by the way, if alpha was irrational, then 2h alpha is still irrational. So application n square alpha mod 1 is uniformly distributed. And you see, it's really modulo van der Korput trick itself is totally trivial thing, which it is also well distributed by appropriate version of, let me add it here, it is also well distributed by appropriate version of van der Korput. And by the way, it's here. So if you believe that van der Korput is true also for well distribution, just get to well-distributed thing after finitely many such differentiations. I mean finitely many if I think about polynomials of any degree. So we did it for n square, and you keep going, right? It's induction. Now it turns out, and that's so good about van der Korput trick, that it has a version for unitary operators, or at least for sequences coming from ergodic theory. And then it allows you to prove interesting things in addition to what we have. So now I think I want maybe to erase it here. And my question to you is there any chance that you don't have to check all H's in van der Korput trick? Can we check only finitely many H's? No, that's unlikely, right? So you can easily build up sequences yourself, which for finitely many H's will satisfy the property, but sequences will not be uniformly distributed. But maybe we don't have to check all the H's. So that's definition. So definition, and it comes from Camae and Mendes-France. Well, somewhere it should be some accent. Maybe in France, do you have any accent here? No. Okay, let it be like this. So Camae and Mendes-France paid attention that it is not necessary to check all the H's, and those H's which is enough to check, this called van der Korput set. So a set E in N is VDC set if it is enough to check, let's call it, give it formula, this, let it be star. To check star only for H in E. I hope, let's talk a little bit to make sure that definition is totally clear. In van der Korput trick, I should go through all possible H's. And it turns out that you don't need all the H's. And if you check only, which is true, and I will give you examples right away. And if it's good only for special H's, this set of good H's is called van der Korput set. And now, since you maybe never dealt with this, you should be puzzled which H's, and indeed, to better understand how things work, maybe you want to see why van der Korput trick is true, and that's something I suggest you do. And by the way, paper of Camae and Mendes-France is not terribly nicely written, but it's so short that you still can get through. They do a very good job, but arrangements are not for everyone. In any case, I think after some effort, it's a very nice paper. And I will give you examples of van der Korput sets. Some of them are already in their paper. So examples of van der Korput sets. First, any set of differences. Same as here. And second, n squared, or more generally, P of n, where P of 0 is 0. The same as there. What was their third? N alpha and square alpha, all right. N alpha and square alpha, etc. So do you see where I'm getting? That there is a curious coincidence that sets which are good for van der Korput trick are the same sets which are good for Poincare recurrence, at least by my examples that I gave you. And so, a priori, it's not clear if these are different notions. What do you think? Are they different or the same? Let's vote. Who thinks that they're the same notion? 1, 2, 3. Who thinks they're different notions? You lost. You lost. Yes, they're different notions. Yeah, democracy works, by the way, pretty well. So, they're different notions, but it's not, until now, it's not clear how to get some decent example. So it was Bourgain who showed that there are different notions in very nice and not totally easy to read paper, and he really constructs it by using very nice probabilistic and harmonic analytic techniques. It remains an interesting question. Take any, so the situation is what we know. What we know that van der Korput is here and recurrent sets are all over, okay? So that's the connection between these two notions. I think that the fact that any van der Korput set is good for recurrence is already in paper of Mendes Franz and Kamai. I'm not sure, but I think so. And by the way, I have a survey with Emmanuel Lessigne, which called van der Korput sets in ZD. It's part survey, part some new results, so plenty of information there. I will give you more examples now. So at least I know some examples of sets of recurrence which are definitely good to be van der Korput sets. But it remains interesting. So this area remains very, very interesting. And I still don't understand well what's going on there. So I think it's strongly related to harmonic analysis and to distinction between properties of positive definite functions and generalized positive definite functions. And we will talk about this almost immediately, okay? But in any case, so fact, any, oh, let's give a definition first. So definition, a sequence Ni in N is ergodic. And again, for convenience, let's assume that Ni goes to infinity, okay? Is ergodic if for any ergodic measure-preserving system X, B, mu T, 1 over N mu of A, T, N, B, not N, T, N, I, goes to mu of A, mu of B. So I think it's natural to call a sequence ergodic if along the sequence Ergodic theorem is true. As a matter of fact, I could postulate this. And that's ergodicity in its really natural form. But it's easier to deal with Poincaré-like things or recurrence-like things. So sequence is ergodic if along the sequence, which is our averages, have correct limit. And you know one example of such sequence, right? So example is X, no, Ni, or just N. Okay, that's surely an example because the Ergodic theorem is true for N. Can you give me any other example? N square is not good. I was waiting for that, thank you. But before N square, what? K times N, that's what I was waiting for. This is also not good. But again, it should come before N square. So let's consider even numbers. Why even numbers are not good? Because you have ergodic system on 2 points. And along even numbers, it's identity. So even numbers are not good, and numbers divisible by 3 will not be good, and so on. Good try. And then your try is also good. Squares, how about that? No. Why? Again, on finite systems, for example, n square mod 3 is not uniformly distributed. Okay? You may want to think why. So we now have we created a problem to ourselves. Other interesting ergodic sequences, I would even add to this, other interesting ergodic sequences of zero density. That would be even more interesting, right? That's why your try with n squares is a good try. So other ergodic sequences of zero density, because if they are, then I can immediately apply it to combinatorics with interest. Okay, any sequence actually applies to combinatorics. But so here is an example. But that's a relatively fresh example. But there are many more. So nth prime to power alpha to power c, integer part. This is nth prime. And c is positive, c is not in n. How do you like this example? Primes themselves don't work. But that's easy. It follows from our previous discussion. Take rotation on 4 points. Okay? Take rotation on 4 points. You see why I take 4 points, because you would say that 2 is a prime. So I take rotation on 4 points. And it's clear that along primes you will never get back. Now there is a candidate. Primes minus 1. So I should add it. Here, 4. Primes minus 1. And I should add it here. 4. Primes minus 1. This is really decent example of set of recurrence. And that's, by the way, very interesting set, right? It's like with n squares, it's not so obvious. With primes minus 1, it's even less obvious why this is good for recurrence. By the way, primes plus 1 is also good. Do you want to generalize this statement? How about primes plus 17? How about primes plus 17? Will it work? Let's vote. Let's vote. Wait. So who thinks that primes plus 17 is set of recurrence? 1, 2, 3, 4. Who thinks that primes plus 17 is not set of recurrence? 1, 2, 3, 4. Oh, it's getting tough. 5. You guys lost. Yes, primes plus 17 is not set of recurrence. But again, for simple arithmetic reasons. Okay, so I leave it to you. What?
They are almost never multiple of 17.
Well, because of Dirichlet theorem about primes and progressions. So in any case, there is some interesting life there, okay? Which sets are sets of recurrence? Which sets are Vanderkorp sets? Is there any difference? And it becomes even more interesting when we go to Ergodic theorem, so we will do it in a moment, maybe. Any questions so far? So this fact, by the way, is relatively recent. It's in my joint paper with...
C
is not integer. Then it's bad. We just now talked about this. Yeah. Primes are not good and squares of primes are not good. Yes?
Why is the same argument not work for prime minus 1?
Which argument?
So the argument that they're not working with modulo.
So because...
You're not working with primes minus 1.6.
No, primes minus 1 is good for recurrence, but again, they do not necessarily have uniform distribution on finite systems.
Why does adding or subtracting for these matter is like this?
Say it again.
Why does adding or subtracting for those matters?
Prime plus 1 is fine for recurrence. Primes minus 1 is fine for recurrence. Any other shift of primes is not good for recurrence. But primes minus 1 are still not an ergodic sequence. Any of the shifts will be even less so, right? Because only 2 come into... You see, sequence is ergodic. That's better, much better than being good for Poincaré. Because you get correct limit. That's a rare event in a way. But there are still zillions of such sequences, and each of them turns out to be automatically Vanderkorp set. So there are many examples of Vanderkorp sets coming from ergodic theory. Are these the only example? No, because sets of differences, for example, are not good for this limiting behavior, yet they are good for recurrence and for van der Kolk. Okay, I will very briefly, are we doing? Time is running. Woo. No, I wanted still to talk about many things. Let's do this. I still wanted to tell you how to prove Sarkozy theorem. And this I have to do. And then I still will have 20 minutes maybe, or less. Okay, so any questions before I erase some things? So why all these things are related to ergodic theory of multiple recurrence, ergodic theory with connections to combinatorics? I will give you an example. I will give you a demonstration now. So how about I will formulate finally, I could do it, should do it yesterday maybe. So here's Furstenberg correspondence principle. This is what connects between recurrence and ergodic theory with combinatorics. So Furstenberg's correspondence principle. For any E in N with density of E positive, there exists measure preserving system X, B, mu, T, and a set A in B with mu of A equal upper density of E, such that for any N1, N2, and K, density of E intersection E minus N1, E minus Nk, bigger or equal, measure of A, intersection Tn1A. I don't have space. Let me write it. I was bigger or equal, the measure of A, intersection Tn1A, Tnka. Is the statement clear? So here's an example for you. So Furstenberg's ergodic theorem says this: for any x b mu t, for any a of positive measure, for any k, there exists n, so that this is true. That's, as you see, far-reaching extension of Poincaré recurrence theory. Poincaré recurrence corresponds to k equal 1. It turns out that you can find joint intersection after n seconds and 2n seconds, or after n, 2n, 3n, and so on. That's Furstenberg's multiple recurrence theory. And it implies, by Furstenberg correspondence, trivially implies Semeredi theorem, right? Because it implies that by this. So you take some set of positive density, create Furstenberg system for it. In Furstenberg system, like in any system, you have multiple recurrence. Then it implies that if d bar of E positive, then there exists n, such that d bar of E intersection E minus n intersection E minus 2n E minus kn positive. But this is Semeredi theorem, because if you take any x in this set, then x plus n is in E, x plus 2n will be in E, and so on. I hope it's obvious, right? Any point of this set is a starter of arithmetic progression of length k plus 1. Okay? People, you are tired. Another 15 minutes, okay? So, because these are really nice and important things, but for you to appreciate, you have to be a little bit more energized. So I will talk louder from now on. Fürstenberg's correspondence allows you to move from function which is far away from being sigma additive or even additive to ideal space where mu, you see, compare these two statements, this one and this one. They're very similar. But here you have genuine sigma additive measure and measure preserving transformation. And here you have a sort of some measure of size, which is all right shift invariant. That's easy exercise. But that's the best thing you can say about d bar. And the statement still is the same, which tells you that Poincare recurrence or generalized Poincare recurrence, see, we proved this theorem for k equal 1 last time. So it gives you a hint that Poincare recurrence and generalized Poincare recurrence are true not necessarily for additive or sigma additive measures. But we observed it already last time. But still, what is easier to deal with? Of course, it's easier to deal with ideal objects, which allow you to introduce all the pleasant strength of functional analysis. So you move very soon to Hilbert spaces and some spectral theory, if it's applicable, and so on, and you start getting things with convenience, and usually which are much stronger than those which can be obtained by more elementary methods. And as I told you already, not everything which we know to do is available by conventional methods. But Fürstenberg theorem is yet another form of Semeredi theorem. You can, and that's an exercise which is not totally trivial, but I leave it to you, to derive Fürstenberg theorem from Semeredi. Okay? Is the exercise clear? So here we are interested in getting Semeredi from Fürstenberg. I claim that you can derive, and by the way, I'm not engaging you in this logicians' polemics that any two correct statements are equivalent. No, I mean getting one from the other in very finitely many lines, okay? And so Fürstenberg theorem does follow from Semeredi as well. So this is just another form of Semeredi theorem, but so conveniently stated that it allows nice generalizations with proofs. Yes?
Are these two statements both difficult to prove? Or is
Which ones?
the correspondence principle and the Ergodic Ramsey
Ergodic Ramsey
Theory?
Theorem is non-trivial statement. I mean, the Fürstenberg's multiple recurrence is non-trivial statement. It's hard to prove. If you are with good ergodic training, then you still need 2 weeks in a class. But Fürstenberg correspondence, I could explain right away, but not today because time is running. It's up to us. It was announced that I deal with such and such topics, but we can reshuffle them, right? Maybe I already started reshuffling them. So I will be glad to explain why, but the nicest proof of Fürstenberg correspondence, which I like, actually involved some elementary facts from, and I don't want to kill you, from C-star algebras, which is a nice example how useful C-star algebras can be. But indeed, you don't need them. So in any case, it's nicely explainable, whereas Fürstenberg proof itself doesn't have a unique, hierarchy, so to say. You have to check for one kind of system, so-called weak mixing systems. You have to check for other kinds of systems, which is complementary to weak mixing. These are rotations on compact abelian groups. That's actually easy part. And weak mixing is today, because of van der Korput trick in the right space, is not so bad. But then to glue them up, that's some work. Okay, but that's very rewarding thing to do. And I think that it reveals a lot about dynamics and gives you good combinatorics. But now let's do another thing. So let me formulate to you Sarkozy theorem. So Sarkozy's theorem, how did we agree to write Sarkozy like this? So Sarkozy, if d bar of E is positive, then there exists n, there exist x and y in E, such that E minus E contains n squared. You remember, I think I formulated it yesterday, did I? And we can reformulate it. Its equivalent form, d bar of E. You have to work to see why this is equivalent, but I like to present things dynamically. So rather than seeing a sort of a static statement that there are 2 points at quadratic distance, let's see it as a moving you set. Okay? So you move by n squared and still get positive. We didn't prove this last time. My n was general, and here is n squared. And here is another equivalent form that's, by the way, already observed by Furstenberg in his original Semeredi paper. And this is this. And here I assume this is for any x, b, mu, t, for any a. And we assume that t is invertible. I don't need it. Okay, let's not worry about this. So these are how in the world you prove it. So let me just, I think I'd rather prove to you now, or explain how one can prove it by using spectral theorem, or big form of it. And maybe this will be close to what we will do today. So I will explain to you how Furstenberg proved this result in his original paper. Unfortunately, that proof doesn't extend so well to more general expressions because it uses spectral theorem, but it's really neat, so let me show it to you. And by the way, so I started saying it and then was distracted. So this result is relatively fresh, and this is joint work with a bunch of people. Let me try to do it alphabetically. Kolesnik, Madrich, Son, and Tichy. I don't think I ever wrote paper with 5 co-authors. That's so in that paper, we not only prove this, but we actually generalize Sarkozy simultaneously to primes and other things. So Sarkozy, by the way, proved another thing, and it's interesting as well. You remember we said that prime minus 1, I don't have space here. Let me try again. E minus E contains prime minus 1. This was proved by Sarkozy. And it can be proved ergodically by using number theory. So I still believe that the correct proof is number theoretical. But in any case, in this paper, we generalize these things. For example, in particular, prime minus 1 square is also there. So that's why your square can be taken to be prime minus 1 itself, and so on. So this paper contains quite a few applications of this kind, but Here we need to establish some non-trivial uniform distribution facts, but which are more general and harder than n-square alpha business. For Sarkozy with square, all you need really is uniform distribution. So let me explain how you can prove that. So fact, easy fact, is that phi of n, which is measure of A intersection T and A, and I want to assume that T is invertible for convenience alone, okay? So is positive definite sequence. So this means that for any xi in C, some xi xj bar phi of I minus j is positive for all n. Non-negative. Thank you. Thank you. Okay, so that's definition of positive. Still, we call the sequence positive definite, but the inequality is not negative. If you are more careful, maybe you should call it non-positive, non-negative. Doesn't sound good. No, non-negative definite. Let's stick to positive definite. In our case, it will be sometimes positive. So this is a definition. Anyone who studies linear algebra should have seen something like this. But anyone who studies functional analysis definitely should have seen something like this. As a matter of fact, modern theory of representations is based on something like this. That this is positive definite thing. And the fact is that by so-called Bochner-Herglotz, and in this case, Herglotz is enough because it's for Z, by Herglotz theorem, and that's really a beautiful thing from harmonic analysis, which I want to propagandize, which some people may not know. Any such sequence is nothing but Fourier coefficients of some measure. Pay attention, this is measure coming from measure space, and this is some measure on torus. So these are different measures, of course. And that's the most basic thing, which if you didn't see before, great. You learned finally something from me. Okay, this is very important and very useful result. And it connects such things with such things. By the way, exercise, mu of A, I really don't check it for you, but it's easy, is positive definite. And this was, by the way, again observed by Hinchin. So Hinchin, as you see, did contribute ideologically to some of the things here. So its hint is that it's not hard, okay? So it's easy exercise to see that it's really positive definite. Because it's positive definite, you can use Herglotz theorem. If you use Herglotz theorem, and I think I will erase it here, so suppose you're interested in this expression, or even n minus m. So this is the same as this. All right, I didn't do anything. I just substituted for this expression. Now I will switch integration and summation. So this is the same as integral 1 over n minus m sum n from m to n minus 1 e 2 pi I n x. And I'm almost there. So let's analyze what we got. So if x is irrational, oh, wait. You know what? I forgot that we are proving Sarkozy. I still can do this. If it's true for all n's, it's true for n squared. So I almost forgot what I'm proving. So I do it for along n squares, and we got this expression. Now, does this look familiar? No. No. But I can take this theorem and then substitute n equal n, not n equals square, put n square for n. It will be subset, so it's surely true. And if I do that, did we see today something like this? We did. People, few more minutes, awake. Did we see it today? In which connection? Uniform distribution if x is irrational. Okay, but most of x's are irrational, right? So if x is irrational, you know what is the limit here? Just 0. So there are still some x's which are rational which mean something. For example, x equals 0. Okay? For example, rational x's. And for them, you have to do some special treatment. And the easiest way to avoid too much of the treatment, replace n by k factorial n. You see, if I replace here so this would lead to expressions of the form k factorial n squared. So I'm going along subsequence of all squares. So what? I'm interested in getting recurrence. If I go along subsequence of all n squares, these are those n squares which are very nicely divisible by anything. That's why k factorial. And if k factorial is large enough, I kill a lot of rational points. You see, suppose x is rational. But my n squared is now k factorial times n squared. So all these rationals, after being multiplied by high degree, high multiple of k, they all collapse. And by the way, the rest of the details is in. What? I want to do this. So now, by the way, I'm hand waving. So okay, so let me just be totally honest. It's not super rigorous proof, but it's idea of the proof. Idea of the proof is this. When you switch the order, you have two types of x's. X's which are irrational, you don't have to care about them. We already know they are uniformly distributed, hence the limit is 0. And then there are x's which are rational. And to do convenient estimates and not to work too hard, they suggest to kill a lot of them, of rational x's, which would have rather small denominators. This will be achieved by putting k factorial ahead of n. What? No, k here is some big number. But when you multiply by such a thing x's with small denominators, you will annihilate them. Right? Suppose it was.
But you must do the sum, then the sum becomes, the average becomes 1.
So that's what I wanted. I wanted positivity of the limit. So don't forget, my goal is to show that the limit is positive. And by playing with this k factorial, we'll see that up to epsilon, it's very positive, a long subsequence. But that's all I need. So by your faces, I see that you're not convinced, but I at least can claim I gave you the idea. And the idea, I think, is properly delivered. The details are left to you. They're nicely done in Furstenberg's book, in many of my surveys, other surveys. It's classical in his original paper. So it's not so hard to complete the details, but the ideas are all there. Using Ergodic Theorem and using killing of the rational spectrum by taking highly divisible n. That's all. And now you feel how uniform distribution helps recurrence. But it doesn't mean that we fully. There are only countably many x's left because I killed already all irrational numbers. So you still.
The integral will not be 0.
Well, there are maybe point masses. Look, that's why I say this is hand-waving proof, but let me just stress, maybe this had to be said. Why do I want to kill rational numbers? Because there are can have point masses, points of positive measure, sitting in those rational points. I have to kill them. What? Then the limit not 0, but there is n equals 0. There is still, the limit will be good one. Then the limit is what you like. Well, I don't want masses, but I have to deal with them. Right. So masses, possible masses at rational numbers, that's an important part of finishing the proof. People, I really can stop now, but I want collectively to guess new theorem, and this will be all for today, okay? 2 more minutes of concentration. So let's try that. So you have, because this will give us something we can start with next time or one of the next times. So you have Fürstenberg correspondence, Fürstenberg recurrence. It's this one. Pay attention. We are so already educated that I start writing things without using quantifiers. When I write something like this, you should guess what are the quantifiers. And by the way, I'm also using that t is invertible for convenience. And that's why I don't put minus there all the time. Now, quantifiers are here. For any system, for any set, for any k, there exists n. So let me stress it. So this is ergodic language. But I'm not sure if it's properly ergodic theory. It will be ergodic theory when the proof will start going. But in the formulation, it's the quantifiers are for all exist. Okay, so no special assumption about my measure-preserving system. Totally universal fact of nature. Okay, so that's why it's Semeredi theorem formulated in ergodic language. That's what it is. In any case, here is one theorem, and here is the other one, which we saw right now. And a similar proof, by the way, can be given for general polynomial. Do you guess what is my question to you? You have two theorems, and that's what happens in ergodic theory of this type, and in Ramsey theory of this type. For any two theorems, usually there is next one which has both of them a special case, and which usually needs new ideas to be proved. Anyone wants to, especially if you never saw such things, any suggestions how to unite these two theorems? Namely, how to formulate, maybe true, maybe not fact, but how to formulate a result which would imply each of them. You want to go home, work fast? Yes, please. Oh, you want to put n inside? Actually, it's possible, but that's not bad. But can I, with your permission, still write it outside? Because I think it's a little bit more suggestive. You see, what you said is totally correct, as a matter of fact. But this is also correct, and usually people guess this. Because it's in a way more streamlined generalization. Now we have to vote if it's true or not. Who thinks it's true? 1, 2, 3. And who thinks it's not true? Okay, so we know it's true. And then maybe we only have to do is to formulate it even more generally, because it's nice already, okay? So it tells you that in Semeredi theorem, the increment, and that's why I insisted on putting 2 and 3 out of the bracket, the increment can be chosen to be square or cube or any polynomial. That's not bad. And by the way, that still is unknown by conventional methods. But this still turns out to be a special case of even more general result. Why don't we try to establish in guessing, this is guess exercise. What could be more general than that? What do you say? Exponents meaning what? These are exponents. What? Oops. That's dangerous because already, for example, this may not work already. Good try, but it may not work. What? Uh-huh. I like that. So that's maybe, how about, so we know this is true, and I will take now T2 and I minus nj. And I'm already not putting quantifiers, but I hope it's clear that we want it for any ni minus nj sequence, right? Now, bad news. It's not always true. So differences are excellent for single recurrence. They already fail for double recurrence. So this, unfortunately, is too optimistic. No, let's stick to polynomials for now, because there is still something to guess there. Why should it be? I'm helping you. Why should it be multiples of the same polynomial? How about this? And of course, pi of 0 is 0 for convenience. Let's vote. Who thinks it's true? And who thinks it's not? Aha! So let's vote again. Like in good democratic society. So who thinks it's true? So actually it is true. And moreover, not only this is true, it's true if ti tj equal tj ti. And this is still not end. So I'm starting now hierarchy of strong and stronger results, which by now goes much more. But we already see that sky is the limit. So if you have single recurrence, but what you suggested is interesting, which single recurrence sequences are good for multiple recurrence? It becomes very curious now, because not all of them are. So is there a property of single recurrence sequences which is better or good enough to generalize to multiple recurrence? I know something about such things, but there is a lot of mystery there. One thing I know, that primes minus 1 are good for multiple recurrence. Differences are not. Things like n alpha, depending how you formulate things, instead of integer part, sometimes it's better to take closest integer. It works a little bit better. Then they're good again. So there is plenty of knowledge, but the whole idea, which we didn't start discussing. So what is then idea of doing such things? Idea of doing such things is not to forget about principles of Ramsey theory. And we will have still to reformulate some of these principles, because so far we were happy to get good configurations in one color, then to get them in large sets, then to get a lot of them. So these questions are equally interesting here. What can we say about n's which are good? Is it just set of positive density? Maybe it's synthetic. Maybe it's delta star. It's not delta star. Maybe it's some other star property. We didn't introduce yet other star properties. These are the right ways of defining large sets, by intersectivity with big families of sets. We'll talk more about this. But in any case, this is still a special case of result which is due to Sasha Leibman and myself, and interpretation of this result is on the level of geometric. That's maybe sometimes preferable way of formulating things. What Semeredi theorem tells you, and that's yet another equivalent form of it, that any large set, any set of positive density, contains a fine image of any finite set. You may want to think why this is true. I will start with this next time. I repeat, Semeredi theorem says, which one? Here. still equivalent form. If d bar of E positive, then E contains A plus BF for any F in N finite. Okay, so you take any finite set, shift it and dilate it. It will be inside your large set. That's what Semeredi theorem is about, geometrically speaking, and that's very preferable language, seeing geometric transformations behind Ramsey theoretical facts. And what polynomial Semeredi theorem says, of this kind, is that polynomial images, so rather than taking linear images, even polynomial images of finite sets, even in our ZD, because I took commuting operators, are still in. And as satisfying as this is, it still leads to new questions which already become subtle. So what can you say about good ends? How large the set of good ends for Semeredi theorem is, for polynomial Semeredi? And it leads immediately to open questions. So very soon, of course, I'm hand-waving and also formulating black boxes type things. So by now, we accumulated a lot of theorems which no chance I will prove to you. I could prove to you Fürstenberg correspondence or van der Korpo trig, but Semeredi theorem itself, no chance. And we'll have to take them as black boxes and still can operate about thinking philosophically about what Ramsey theory and Ergodic Ramsey theory provide you with. And before we will finish this course, you will learn a little bit about ultrafilters and how they allow to use Poincaré recurrence theorem, again, ideology of Poincaré recurrence theorem, and connection. It's all abelian here. Is there any connection to nilpotent groups? Is there any non-commutative mathematics behind it? Turns out there is. And I don't know, but maybe we will touch on more general groups like amenable versus non-amenable and what is known and what should be of interest there, because why should we stick to Z or ZD? Okay, so this is still, today, it's still small portion of what is known, and I will keep telling you as long as you will be interested to listen. Thank you. Oh, okay. Good that you told me. Yeah. Okay. See, those of you who will survive until tomorrow, see you tomorrow then. So my talk is, next talk is like today, yeah. Tomorrow. Yeah. Good that you, but maybe you want to announce, there are a few people who didn't come. I see. I see. Good to know. Okay. See you tomorrow.
Hoje deu errado?